Hello everyone, this is Sai from CSIT. Today in this presentation I am going to explain about the ultrametricity to infinite matrices. The contents in this presentation are an abstract, introduction, divergence sequence, lemma, theorem, proof and few references. Let's start with the abstract. In this short note, it is provided the existence of infinite matrices that not only preserve convergence and limits of sequences but also convert every member of some dense vector space consisting, except for 0, of divergent sequences into a convergent sequence. If we go for the introduction, if this method is carried out by an infinite matrix A is equals to Aij, where I and j are greater than or equals to 1, then A transform of a sequence of scalars where x is equals to x, small x, is given by capital Ax is equal to small ax, provided that every series Axi is equals to infinite j is equals to 1 Aij xj, where I is equals to 1 2 up to n converges. Hence A can be viewed as linear operator. A dA tends to omega, where omega and dA denote respectively the vector space Kn of all scalar sequences and the subspace of all sequences for x belongs to omega, for which Ax belongs to omega, that is for which every series Axi where I belongs to n converges. Limit I tends to infinity is equals to limit Ax limit I tends to infinity is equals to limit Ax Axi, where I tends to infinity is equals to limit x I tends to infinity. For all x is equals to x I is greater than or equals to 1. Divergent sequences that become convergent. In order to establish our result, it is convenient to fix some notation and to recall a number of facts from functional analysis and set theory, and also from the modern theory of lineability. The set omega will be endowed with the topology product, that is one of the coordinate-wise convergence. Then omega becomes an F-space that is completely metrizable topological vector space. It is separable because, for instance, the sequence in C double naught with entries q, the rationals, are q plus iq according to k is equals to r or c respectively. From a dense countable subset of omega, here C double naught denotes the family of sequences with finitely many non-zero entries. A standard application of Bayes' category theorem shows that dimensions of omega is equals to C. The cardinality of continuum, a family A lambda, A double lambda belongs to lambda of infinite subsets of n is called almost disjoint. A lambda intersection A mu is finite whenever lambda into L is equals to mu. The usual procedure to generate such a family is the following. Denote by Qn is Qn where n is greater than or equals to 1, an enumeration of rational numbers. For every irrational A, we choose subsequence Qn into k where k is greater than or equals to 1 of Qn where n is greater than or equals to 1, such that limit k tends to infinity Qn into k is equals to A, and define A is equals to nk where k is greater than or equals to 1. By construction, we obtain that A double A belongs to R by Q is an almost disjoint uncountable family of subsets of n. Let's look it in the lemma. Suppose that X is separable infinite dimensional F space and that A and B are subsets of X satisfying the following properties. A is stronger than B. A intersection B is equals to null set. A union 0 contains some vector space whose dimension equals to dimension of X is equals to C. B union 0 contains some dense vector subspace of X. Then there exists a dense C-dimensional vector subspace of X contained except for 0 in A. We are now ready to state our theorem by subsequence nk, where k is greater than or equals to 1. We mean strictly increasing sequence where n2 is greater than n1, n3 is greater than n2 up to n of natural numbers. The theorem. Assume that A is equals to Aij, where I and j is greater than or equals to 1 is an infinite matrix over the scalar field K, satisfying the following properties. For every j belongs to n, the sequence Aij where I is greater than or equals to 1 converges. There is a subsequence nk where k is greater than or equals to 1 is a subset of n such that for each one of its subsequences mk, k is greater than or equals to 1 is a subset of nk where k is greater than or equals to 1. We have b1, the sequence a sigma imk where k is greater than or equals to 1 is summable for every I belongs to n, and then there exists a dense C-dimensional vector subspace of omega, all of whose non-zero members diverge but their A transforms converge. And the proof. Let's note the family of divergent sequences X omega such that Ax is well-defined convergent sequence, that is A is equals to A inverse into C whole by C. For every sequence X is equals to Xn where k is greater than or equals to 1 belongs to omega, we denote by sigma of x its support, that is sigma of x is equals to n belongs to n is to xn by is equals to 0. If we have finitely many sequences x to the power 1, x to the power 2 up to x to the power p belongs to omega by c double naught, such that the family of their supports sigma into x to the power 1, sigma into x to the power 2 up to sigma into x to the power 1 is almost disjoint. Such sequences are linearly independent. Finally, one may wonder whether there are TS matrices converging every divergent sequence into a convergent one. This is far from being true. As a matter of fact, given a TS matrix A, there is a sequence x is equals to xn omega with xn is equals to 1 for all nn whose A transforms Ax diverges. It remains to prove the condition of lemma 2.1. Firstly, observe that C double naught is a subset of dA since C double naught is algebraically generated by the basic sequences e to the power I is equals to delta jn, n is greater than or equals to 1. In this j belongs to n, and each a e to the power I is simply the jth column of aij where I is greater than or equals to 1 of A. Moreover, these columns being convergent due to A, we get by linearity that AB converges for all V C double naught. From the facts that A acts linearly and the sum of convergent sequence and a divergent one diverges, we obtain that A inverse plus C double naught as required. Finally, the lemma 2.1 yields a conclusion. Notice that every TS matrix satisfies conditions A and B1 of theorem 2.2 indeed. Each column tends to 0 and B1 is fulfilled with an subsequence n of nk is a subset of n satisfied by, for instance, the TS matrix A0 is defined in section 1. Take nk is equals to k square. This would give 0 as the limit for all sequences of B2. So, excluding the existence of TS matrices, converting a large amount of divergent series in convergent ones. And here are the few references where you can deeply look at it in the topic, and then thank you everyone.